Okay, so the first part of the homework was to show that an ideal in a commutative ring is the whole ring if and only if it contains the element 1, the multiplicative identity. Now this is an if and only if question, so this proof should have two halves. So let's just choose one way or the other. Perhaps I'll do the forward implication to begin with. So let me just say what I'm going to do. So first, show that if I equals R, then 1 is an element of I. Well, I'll hit on the easy half to begin with. If I is the whole ring, well, given that the whole ring contains the element 1, then 1 is in I. So, I mean, all I need to say is that 1 is in R. So if I equals R, then that means 1 is in I. Okay, so now I look at the other direction. So now I want to show that if 1 is an element of I, then I must be the whole ring. Well, I didn't really need to write all that. I could just say, I could just write, conversely, suppose that 1 is an element of I, then what we want to deduce from that is that I equals R. Now these little things like this, sort of breaking up the proof and taking stock of what we're assuming and what we're trying to deduce from that, I mean this gets us a long way, and you should always do this kind of thing. I mean, it takes no effort to write this down. It doesn't take any thought about what's going on to just write this and see what it is that we have to do. Now, having seen what it is that we have to do, though, we have to think about how to do it. Now, I is an ideal of R, so we ought to use that fact somewhere along the way. If we produce a proof that doesn't use the fact that I is an ideal of R, that probably means we've done something wrong. And it's certainly not the case that any subset of any kind on containing 1 has to contain everything else as well. Now, and again, it costs nothing to just recall the definition of an ideal. I mean, if you can't remember the definition of the ideal, an ideal, you can look it up. And that's something everyone can do. So if you look it up, you'll find that an ideal is an additive subgroup of the ring that's closed under multiplication by the ring. So, perhaps I'm going to use then the fact that it's an additive subgroup. So, from the fact that 1 is in I, we want to deduce that everything else is in I. I mean, certainly I is contained in R. It's really for R to be contained in I. That's the thing we need to prove, that everything in R is also in I. Now, it's not really enough to use that I is an additive subgroup. Additive subgroup, okay, because that gets 0 into I. And given that 1 is in I, and so it's going to be, it'll get -1 to be in I. And it'll get 1 plus 1, and 1 plus 1 plus 1, and -1 plus -1 plus -1. So we'll have a sort of homomorphic image of Z, the integers, sitting inside I, given that I is an additive subgroup, just starting from the fact that 1 is in I. But that's not enough. I mean, suppose, for instance, that we were working in a polynomial ring then that polynomial ring isn't generated by all these elements that we generate from 1 using addition and inverses. There's more than that. So the property we must use of the ideal is this closure under multiplication by the ring. So given any element of the ring, how do we show that that belongs to the ideal? Well, we simply write it as r times 1. And since 1 is in the ideal, r times 1 must also be in the ideal because it's an ideal. Hence, indeed, I is equal to r.